All right, let's take a look at 4.5. I'll include these notes in the module so that you can kind of print them off and follow along, or write on them using your tablet or whatever. Um, but 4.5 is about applications of maxima and minima. Okay, and so generally I'm going to follow these guidelines that are in your book. I just kind of copied these from the textbook, but I think they're good guidelines for solving these sorts of applied problems. So generally speaking, I'm going to start off by drawing a picture of the scenario. Then I'll try to find a formula for the quantity that I'm supposed to maximize or minimize. And this is going to work out much easier if we can describe that formula in terms of a single variable. So we'll try to use the information in the problem to express the quantity to be maximized or minimized as a function of a single variable. And then another important step, and this is one that I sometimes forget to do, but it is an important step, and that is that we need to find the interval of possible values for the variable based on the physical restrictions that are in the problem, and you'll see what I mean. Um, for example, if we're talking about a length, then we know that it's got to be a positive value. So like if you're trying to minimize something and it involves a length, and the only critical value you come up with is negative, well, you know that you can disregard that, right? Anyway, um, and then finally we'll use the techniques from 4.4, right, to obtain the maximum or minimum value, if one exists, right? So without further ado, let's just look at, I think I've got probably 7 examples. Yeah, I think 7 examples here. So let's get to it. This first one says a garden is to be laid out in a rectangular area and protected by a chicken wire fence. What is the largest possible area of the garden if only 100 running feet of chicken wire is available for the fence? Okay, so this is a pretty easy one to draw out, right? We've got a rectangular garden. And maybe, I'll call the length x and the width y, or, whatever. Um, what are we trying to maximize? It says, what is the largest possible area? So we're trying to maximize the area, right? Well, the area is going to be length times width, okay? Now, we said that we wanted to express the thing that we're trying to maximize. In this case, we're trying to maximize the area. We want to try to express that in terms of a single variable, and here we have 2 different variables, right? So let's see if we can use some more of the information in the problem to rewrite this as a single variable. We're told that we only have 100 running feet of chicken wire available. So that means that we only have 100 feet of fencing available to us. So the perimeter can be no more than 100. Okay? So the perimeter has to be less than or equal to 100, I guess you could say. Well, what is the perimeter, right? The perimeter, how would we calculate it, that is? We would say the perimeter is x plus y plus x plus y, in other words, 2x plus 2y, right? And that perimeter can be, at most, it can be 100, right? So we can say 100 equals 2x plus 2y. So I can solve this equation for y and get y in terms of x, and then I'll be able to plug that in here. So solving this thing for y, we would subtract the 2x and then divide by 2, right? So y is 50 minus x. So I can take this now and I can plug it back in for y here, and I can see that a is x times y. And now I've done it, right? I've expressed the area in terms of just a single variable. So that's good. So the next thing that we should do, I suppose, is so we've drawn a picture, found a formula, we've written it as a single variable. Then let's find the interval of possible values for this variable. Well, the variable is x, right? And since x is a length, the smallest x can be is 0. So we'll say note that x has to be greater than or equal to 0. But x also has an upper restriction, right? Because y also has to have a certain length. That is 50 minus x has to be more than 0. Okay, so if 50 minus x has to be more than 0, then that would mean x has to be less than or equal to 50. Right? So x really has to live between 0 and 50. Okay? Alright. So now let's maximize our function. By the way, I'm going to go ahead and distribute that x. This is 50x minus x squared. So the derivative, a prime, or you can call it dA dx if you like, but that's going to be 50 minus 2x. And then if I set that equal to 0 and solve so that I can find my stationary points, I'm going to get 50 equals 2x, so then x is 25. And that's my only critical value. However, I'm only interested in maximizing this function on this closed interval between 0 and 50. And so the endpoints might be absolute extrema as well. So I'm going to check the endpoints as well as my critical point here. You can do this using like a table or whatever. I'm just going to do it like this. I'm going to say, well, what's the area when x equals 0? When x equals 0, the area is 0 times 50 minus 0. Well, that's just 0. So that doesn't do us any good. What's the area when x is 25? Well, then it would be 25 times 50 minus 25. In other words, 25 times 25, which is 625. I should have known that, but I had to use my calculator. Okay, and then what's the area when x is 50? That would be 50 times 50 minus 50. Well, that's just 0 again. Okay, so clearly this maximizes things, right? So what question were we supposed to ask? What is the largest possible area? Okay, so the largest possible area is 625 square feet. Okay, and there's our answer. That happens whenever you use a length of 25, and if you're using, I forgot if I called this length or width, it doesn't matter, right? But if we call x 25, y would also have to be 50 minus 25 is 25, right? So you actually get a square, right? The shape that maximizes the area is actually just a perfect square, which maybe isn't surprising to you, right? But there you go. Let's look at another. So number 2 says, an open box is to be made from a 16-inch by 30-inch piece of cardboard by cutting out squares of equal size from the 4 corners and bending up the sides. What size should the squares be to obtain a box with the largest volume? Okay, well, let's draw a picture. So we have this square, or this rectangle rather, that's supposed to be 16 inches by 30 inches. Okay, but we're going to cut out squares from each of the corners. So we're going to cut out squares from each corner. Okay. We're going to cut out squares of equal size from each corner, and then that's going to allow us to you see, that'll allow us to bend up this little flap, and this flap, and this flap, and this flap, and it'll make a little box with an open top, right? So it's an open box. Okay, and we want the box with the largest volume. So it says, what size should the squares be to obtain the box with the largest volume? So here's what I'll do. So I'll call this length x, and that means this length also has to be x, right? Since these are squares. And you know, we can do that with all the other squares as well, since they have to be equal in size. They're all x by x squares. So 16, you know, gets us all the way. It's like the entire length of the original piece of cardboard. But now what's the length of this piece right here? Well, it would have to be 16, it would have to be 16 minus x minus x. In other words, 16 minus 2x. So this little piece right here is 16 minus 2x. And same with this one. What about this one? Well, we know that from here to here is 30. So just this little piece right here to get us from this to this would have to be 30 minus 2x. Okay. So that's important because when we're describing the volume of the box that's going to be formed here, right? Because we want to maximize the volume. So when we're describing the volume of the box, the volume is, you know, length times width times height. Well, what's going to be the length of that box? It's going to be, once we fold up all the flaps, the length is going to be, right, you can kind of imagine, right, the length is going to be 30 minus 2x. The width is going to be 16 minus 2x. And the height, well, the height is just going to be x, right? It's going to be x. Yeah, it's going to be x. Okay, so there we've done it, right? We've expressed the volume in terms of just a single variable, x. Okay, I'm going to want to differentiate this thing, and so in order to avoid having to use product rule a bunch of times, I might actually want to go ahead and FOIL this out, or you know, multiply it all out. So 30 times 16, well, 3 times 16 is 48. So 30 times 16 would be 480. 2 times 30 is 60. 2 times 60, or yeah, 60. 2 times 16 is 32. 60 plus 32 would be 92. So I'm going to say minus 92x. And then negative 2 times negative 2 is positive 4x squared. And of course, we're multiplying that all by x, which I suppose I could have done all at the same time, but 480x minus 92x squared plus 4x cubed. That's the volume of that cardboard box that we're going to get, right? Okay. So the next thing that I'm going to want to do is find sort of the restrictions on x, I guess. And once again, x is a length, so we know that x has to be, you know, greater than 0. We also know that, you know, x is this little piece that we're cutting out from each corner. If x, and this entire side is 16, it's the smaller of the two sides. So x could be like 5, then we would cut out 5-inch pieces from each corner, and we would be left with a 6-inch piece in the middle, right? Or x could be 7. Then we would cut out 7 inches, that's 14 inches in total, and we'd be left with 2 inches in the middle. But if we cut out 8, if x was 8, we'd be cutting out 8-inch pieces from each corner, and we would be left with nothing in the middle, right? So x has to be less than or equal to 8. If x were 9, that's an impossible scenario, right? So x has to be less than or equal to 8. So we know that this is really the restriction we're working with, right? X has to be between 0 and 8. Okay, well, so let's differentiate, right? So dv dx, or you can call it v prime, whatever you prefer, is going to be 480 minus 92 times 2 is 184. I wish you guys were here. I wish we were meeting face to face, because I make so many mistakes, as you've noticed, I'm sure. If you've been watching these videos, you know that I make a lot of mistakes. And it's much nicer to have someone checking your work and letting you know when you make a silly mistake in arithmetic. But I think that's correct. Okay. Now, we need to set this equal to 0 and solve. I think 12 goes into all of those numbers. Does 12 go into 184? 184 divided by 12. Oh, it doesn't. Well, but 6 probably does. 184 divided by 6. 6 doesn't. Shoot. 184 divided by 3. 3 doesn't. Well, okay. I wonder if 4 does. 4 into 184. 4 goes in. So I guess 4 is the best we can do. Alright, so I'm going to set this equal to 0 and solve. So I'm going to rewrite this in descending order and factor out of 4. So I'm going to have a 3x squared, and then, I just did it, minus 46x, and then 480 divided by 4, 120. Oh, yeah, of course, 120 equals 0. And can we factor that? I mean, if we can't, we'll just use quadratic formula, but oh man, that seems so nasty to have to try to factor that thing. Well, let's try. I mean, I know that it's got to be a 3x. What are some factors that give us 120? I mean, the first thing that springs to my mind is 10 and 12. I could put if I put a 12 here, that would mean that I'd be able to factor out another 3, which I can't. So the 10 must have to go here. I'm going to use pencil so I can guess and check a little. 12, sorry, 10 and 12. And let's see, 3 times 12 is, see, that's going to do it. 3 times 12 is 36, and then minus another 10 will give us a 46. So yeah, oh, look at how lucky we are. 10 and 12. If that hadn't worked, we could have used the AC method, 3 times 120, and then, that would have been kind of nasty. I probably just would have resorted to the quadratic formula, to be honest with you. But anyway, so there we go. So possible critical values would be, if we set 3x minus 10 equal to 0 and solve, we're going to get 10/3. Or if we set x minus 12 equals to 0 and solve, we get x equals 12. So those are the possible, those are the critical values. But notice that 12 falls outside of our interval, okay? So we know that we're not really concerned about that one. That means the only critical value we really need to test is 10/3, and of course the endpoints 0 and 8. So let's do that, right? So if we plug in 0 to the volume, I'm going to use the original factored version. So this is 30 minus 2 times 0 times 16 minus 2 times 0 times 0, which is just going to be 0. Okay, so that's not very interesting. What about 10/3? If we plug in 10/3, what do we get there? Okay, so we get about, so we'll just say this is about 725.9. Okay, and then finally, what if we use 8? I should stop writing this stuff out because I think you understand where it's coming from. But anyway, so we'd have 30 minus 16 times, 16 minus 16 is going to be 0 again. Okay, so this is just 0. Oh, well, there you go. So obviously this is the thing that maximizes the volume. So now what question are we supposed to answer? It says, what size should the squares be to obtain a box with the largest volume? So it looks like the squares should be 10/3 by 10/3 of an inch, right? Okay, and that's that one. So hopefully you kind of get the idea with what we're kind of doing here. The problems can get a little more challenging though. Let's look at the next one. So it says an offshore oil well located at a point W is 5 kilometers from the closest point A on a straight shoreline. Whew, okay. Okay. Oil is to be piped from W to a shore point B that is 8 kilometers from A by piping it on a straight line underwater from W to some shore point P between A and B. Oh, are you lost yet? Because I'm lost. And then on to B via pipe along the shoreline. If the cost of laying the pipe is $1 million per kilometer underwater and $500,000 per kilometer over land, where should the point P be located to minimize the cost of laying the pipe? Woo, definitely going to have to draw this out. So, it says an offshore oil well located at a point W is 5 kilometers from the closest point A on a straight shoreline. So, here's what I'm imagining. Here's the shore. And maybe this is A, right, along the shoreline. And then we have the offshore well, and it says that it's 5 kilometers from the closest point A. So the closest point, that means that it would be directly perpendicular, right? So maybe W is up here, okay? And we know that this distance is 5 kilometers. Very good. Okay. It says oil is to be piped from W to a shore point B that is 8 kilometers from A. So it's a shore point, so it's another point along the shore, right? So maybe B is here, and this is supposed to be 8 kilometers, right? From here to here is 8 kilometers. Okay. Okay. So oil is to be piped from W to B by piping it on a straight line underwater from W to some shore point P between A and B. Why not just go directly to B? Okay, because the cost of laying the pipe underwater is twice as much as the cost of laying pipe over the land. So they kind of want to get to land as quick as possible. So that kind of leads me to think, why not just go to A and then B? Well, that's gonna mean more piping. Okay, so we've got okay, this is a good problem. Hey, I like this. All right, so it's got to be, so it's going to be piped to some point between A and B. Call the thing P. So there's going to be some piping that goes from W to P, and then some more piping that goes from P to B. Okay, got it. Okay, I think I've got my brain around this problem now. So now the question is, where should P be in order to minimize the cost of laying the pipe? Well, what's the cost of laying the pipe, right? So the thing that we want to minimize is the cost. So so the cost of laying the pipe, we know that it costs $1 million per kilometer underwater. So if we know this length right here, then we can multiply that by $1 million, and that would be the cost of laying this length of the pipe. And then this length of the pipe, we would multiply by $500,000, and that would be the cost of laying that portion of the pipe. So the total cost would be this cost plus this cost. And so what that really boils down to is finding an expression for this length and this length. So let's see if we can do that. We don't know where P is supposed to be located. Let's just call the distance from A to P x. Alright? So if we call the distance from A to P x, then the distance from P to B would have to be 8 minus x, right? So this distance here is 8 minus x. Okay, so we know that length. Now, what about this distance? Well, we can use Pythagorean theorem, right? We know that leg squared plus leg squared equals hypotenuse squared. So the hypotenuse is the square root of x squared plus 25. Right? Just using Pythagorean theorem. Okay? Good. Now, in order to avoid working with huge numbers, 1,000,000 and 500,000, I'm just going to give my formula for the cost of laying the pipe in millions. So in other words, I'm going to say the cost of laying the pipe is 1 times the length of the underwater piping plus, well, 500,000 is half of 1,000, right? So we say half times the length of the shoreline piping, right? So this is the cost in millions, right? So this is in millions. So this is the cost in millions of laying the pipe. And notice that it's all expressed in terms of a single variable already, so that's nice for us. We can simplify it a little, right? Okay, something like that. Good. Do we have any restrictions on x? Well, we sure do, right? Like, for one thing, x has to be x is the distance between a and p, so it has to be at least 0, right? So it has to be greater than or equal to 0. But also x can't be more than 8. It wouldn't make sense for them to pipe it all the way out to here just to backtrack. That would be way too much piping. So x has to be between 0 and 8. Oh, just like the previous problem. How interesting. Okay, well, let's differentiate. I'm going to call this c of x because that helps me later on when I go to plug in values. Anyway, c prime of x is going to be, let's see, it's going to be 1/2 times x squared plus 25 to the negative 1/2 times 2x. The 4 is going to disappear. And then minus 1/2. Okay, let's see if we can clean that up. So I think the 1/2 and the 2 are going to cancel. We'll end up with the well, then again, maybe I don't want to cancel it because I might want to combine my two fractions here. So here's what I'm going to do. I'm going to call this 2x minus 1 over 2 times the square root of x squared plus 25. There you go. Right, this ends up in the denominator as a square root. This ends up in the numerator. This ends up in the denominator. And then we subtract the 1/2. Oh, but I'd have to have I still wouldn't have common denominators though, would I? So it would actually be 1 times, oh, I skipped too many steps, right? Because really I'd have to have this. I'd have to do root over root x squared plus 25, right? So really I'd have 2x minus the square root of x squared plus 25. Okay. So as far as critical values are concerned, so I do actually have potentially a place where this thing is where this is not differentiable. Although I don't think that actually does happen, right? Because when we square something, it's positive, and when we add something to that, it's positive. So this denominator is never going to be 0. Okay. So the only real issue, I suppose, is if the numerator is equal to 0. Okay, so I'm going to set 2x minus square root of x squared plus 25 equal to 0, and then solve. So so I'm going to get 2x equals square root x squared plus 25. I'll square both sides. And then I would divide by 3 and take the square root. So I'm going to get x equals plus or minus 5 over root 3. Okay, good. Notice that negative 5 root 3 falls outside of our interval, so we can ignore the negative version. But also, we should check for extraneous solutions, because anytime you square, see here I squared both sides of the equation, right? And anytime you do that, you introduce the possibility that you have some extraneous solutions. So let's see, if we plugged in positive 5 over root 3, ugh, how nasty. Well, we would get 25 over 3 plus 25. So that would, 25 is 75 over 3. 25 plus 75 is 100, so this would be 100 over 3. Square root of 100 over 3 would be 10 over root 3. And 2 times 5 root 3 would be 10 over root 3. So I think it works when we plug in the positive version. When we plug in the negative version, oh, that's not going to work, right? Because then we're going to get negative 10 over root 3 over here. And on the right hand side, this is always a positive number, so it can't possibly hold up. So that's 2 reasons to reject negative 5 over root 3. So really, we're only going to take the positive one, right? So I'm going to ignore the negative 5 over root 3 for that reason. Okay, so we should check our endpoints, and we should check positive 5 over root 3. So let's see. What is the cost when x equals 0? So when x equals 0, we would go straight from W to A, and then straight from A to B, right? What's the cost of doing that? That would minimize the amount of piping under the water, but it wouldn't minimize the distance, and so there's some give and take, right? So what's the cost? That would be the square root of 0 squared plus 25 plus 4 minus 1/2 times 0. So that's just going to be $9 million, right? So $9 million. Okay. What's the cost when x is 5 over root 3? I'm not going to bother writing the whole thing out. I'm just going to punch this into my calculator. Let's see. We have square root of 5 over root 3 plus 25 plus 4 minus 1/2 times 5 over root 3. Okay, so that comes out to about 7.8. I mean, the exact value is too nasty to even write down. So I'm going to say this is about 7.8. Okay, so that's 7.8 million. Okay, and then what's the cost when x equals 8? So when x equals 8, that means we go straight from W straight to B, right? But all of that minimizes the distance, it minimizes the amount of piping, but it maximizes the amount of piping underwater, which is more expensive than piping over the land. So let's see what we get when we do that. We would have, okay, so we'd have square root of 8 squared plus 25 plus 4 minus 1/2 times 8. Okay. So that comes out to about 9.4. I'm just going to say it's approximately 9.4. So this is $9.4 million. Okay, so what's the winning strategy, right? What minimizes the cost? Well, that would be this one right here, right? So it's asking, where should point P be located to minimize the cost? Well, point P should be located at 5 over root 3 kilometers from A, right? So we'll say P should be 5 over root 3, which is approximately 5 over root 3 is approximately 2.89. from point A. Okay, so that's very interesting, I think. That's very interesting. Okay, I like it. Okay, so that was example 3. Maybe I should split this into 2 videos. How long have we been going? We've been going for 34 minutes. Yeah, I might have to split this into 2. Let's see. How many more examples we have? 4, 5, 6. Oh man, we've got 4 more. Well, okay, let's go. Find the radius and height of the right circular cylinder of largest volume that can be inscribed in a right circular cone with radius 6 inches and height 10 inches. What? Okay, let's draw this. So find the radius and height of a right circular cylinder of largest volume that can be inscribed in a right circular cone with radius 6 inches and height 10 inches. Okay, so so the cylinder is inside the cone. So let me draw the cone first. So the cone is going to look something like this. Okay? And then the cylinder is going to be inscribed inside of it. So so maybe, the cylinder looks something like this, I suppose. Okay. That's really kind of confusing, I think, but that's the best I'm going to be able to do, I think, when it comes to drawing this. So, okay, we know that the cone has a radius of 6 inches, and it has a height of 10 inches. Okay. And that's all we've got. So we want to find the largest volume for the cylinder. Okay. Maybe I'll do it in blue so that it matches the cylinder, right? Well, the volume of a cylinder is the area of the circle multiplied by its height, right? So it's pi r squared h. Okay, so I guess I'm labeling this from here to here is h, and this from here to here is r. Okay, I've got to try to rewrite this in terms of a single variable, and so that means that I need to find a way to relate h and r together. So here's what I'm going to do. So let's just imagine, right? So if you split this down the middle so that we're dealing with all the radii, you notice that you get right triangles, right? You have a right triangle here, and then another smaller right triangle here, and they're similar triangles. So I'm just going to redraw that, right? This is what you've really got. This is 6, this is 10. But then you've got a smaller little right triangle inside of it. Okay? And from here to here, maybe I should do that in red, I suppose. Now the colors are just getting confusing, right? But from here to here was h. And that means from here to here is 10 minus h. Okay? However, this part is the top of the cylinder, right? It's the top. The bottom of this little triangle is the top of the cylinder. Okay? It's the radius of the cylinder, I guess I should be saying. So that's the radius. Okay, so using similar triangles, I can say 10 minus h over r, or 10 minus h is to r, as 10 is to 6. Okay, and then I can use that to relate h and r together. So let's solve. Let's solve for. Which one do we want to solve for? I think maybe h. I mean, it doesn't matter. You can do it either way, but I'm just trying to see which one's because if I solve for r in terms of h, then I have to square the expression. I'm not sure I really want to do that, so I'm going to solve for h. Okay, so I'm going to say 10 minus h equals, this reduces to what? 5/3, right? 5/3 r. And then if I add h and subtract that, I'm going to get h equals 10 minus 5/3 r. So that's not bad, okay? Okay, so I can come back up here now, and I can replace h with 10 minus 5/3 r. So the volume is going to be pi r squared times 10 minus 5/3 r. Or in other words, that would be 10 pi r squared minus 5/3 pi r cubed. Okay, now we can differentiate. So I'm going to just kind of box this in. It was its own little thing. That way I can continue on with my work up here. But this is where I got the that. Okay. Oh, what about restrictions here? So as far as restrictions are concerned, I've expressed everything in terms of r. So as far as r goes, r has to be less than 6, right? That would happen if the height were 0. So r has to be less than or equal to 6. And I suppose you could go all the way to the top and make r equal to 0. So r has to be between 0 and 6. So notice that this is the restriction, right? R has to be between 0 and 6. Okay, now let's differentiate. So derivative with respect to r now is going to be 20 pi r minus 5 pi r squared. Okay, and then I'm going to set that equal to 0 and solve. I can take out a 5 pi r, and I would be left with 4 minus r. So I get two solutions. I get r equals 0 or r equals 4. That's not very surprising, okay? So now I can test these out along with the endpoints. 0 is already an endpoint, so that's kind of nice. But I can look at volume when r is 0. That's going to be pi times 0 squared times whatever. That's just going to be 0, right? I can look at the volume when r is 4. That's going to be pi times 4 squared times 10 minus 5/3 times 4. Let's see about how much that is. Yeah, okay, sorry. So 16 pi times 10 minus 20/3, we'll say. So that's 160 pi over 3, which is approximately 167.6, we'll say. Okay, and then what about when r is 6? I suppose you're going to get a volume of 0 again, right? Yeah, because notice that if you plug in 6 here, the 3 will cancel a 3 and leave a 2. 2 times 5 is 10, and 10 minus 10 is 0. So you're going to get 0 again. So obviously, the cylinder of maximum volume is going to be 167.6-ish inches, cubic inches, and that happens when the radius is 4 inches. What were we supposed to do? It says find the radius and height. Oh, okay. Well, so the radius is 4 inches and the height is well, we said the height would be 10 minus 5/3 r. So if r is 4, 5 times 4 is 20, so this would be 10 minus 20/3. That would be 30 thirds minus 20 thirds, so 10 thirds, and the height is 10 thirds inches. Okay, and there you go. You know what? I'm not going to split this into 2 videos. This is just going to be I think this is just going to be an extra long video. I'm not exactly sure why I would split it up, really. Okay, next one. A closed cylindrical can is to hold 1 liter, that's 1,000 cubic centimeters of liquid. How should we choose the height and radius to minimize the amount of material needed to manufacture the can? Goodness gracious, wow. Okay. So the can has to hold 1 liter. Okay, so 1,000 cubic centimeters. Okay, so once again, we have this cylinder. Right, it's going to be a cylindrical can, but and we know that it needs to hold 1 liter of liquid. But we want to minimize the amount of material needed to manufacture the can. So we're not trying to minimize the volume of the can. In fact, the volume has to be 1,000 cubic centimeters. What we're trying to do is minimize the material. That means we have to minimize the surface area of this cylinder. Well, what's the surface area going to be? Well, it's going to be the area of the circle on top and the area of the circle on bottom. And then it's going to be the area of this, like, imagine that you cut this in half and then unrolled it. It would just be a rectangle, right? That rectangle would be whatever the length of the rectangle would be whatever the height of this can is, and the width of it would be, well, it would be whatever the circumference of the circle is. Well, that would be 2 pi. So if we call this, if we call the radius r, then it would be 2 pi r. Okay, so the surface area is 2 times the area of the circle on top and bottom, so that's 2 times pi r squared, plus the area of the rectangle. That's going to be 2 pi r h. Okay. This is what we're trying to minimize. We're trying to minimize the surface area. And unfortunately, we've got 2 variables in there, right? So we've got to try to eliminate one of them. Well, here's what we can do. We can also describe the volume of the cylinder. The volume is going to be pi r squared h. And here's the restriction, right? The volume has to be 1,000 cubic centimeters. So so I'm going to say 1,000 equals pi r squared h, and then I can solve for h, right? So I can just say h equals 1,000 divided by pi r squared. Okay, so when I do that, now the formula for the surface area becomes 2 pi r squared plus 2 pi r times 1,000 over pi r squared. And that's kind of nice because that simplifies a little bit more. I'm going to have 2 pi r squared plus the pi's will cancel, one of the r's will cancel. We'll have 2,000 over r. Okay, so that's what we need to minimize. What about restrictions here? I don't think there are any. We can make the radius as small as we like, and we can make the radius as large as we like. Well, the radius does have to be, okay, so we have that restriction at least. But we don't have any upper restriction. We can make the radius as large as we like, as long as we make the height small enough so that the volume is still 1,000 cubic centimeters. So no restrictions on the upper end as far as the radius is concerned. So let's differentiate. This is 2,000, oh, I should have said minus, right? Because it's 2,000 times r to the negative 1. So that's going to be negative 2,000 times r to the negative 2. I'm going to factor out an r to the negative 2. Maybe I'll factor out a 4. R to the negative 2. We'd be left with pi r cubed minus uh, 500, minus 500, of course. Or in other words, this would be pi r cubed minus 500 over, oh well, I guess it would be 4 still up here, over r squared. Good. So, this place, or this function is not differentiable at r equals 0. Okay, so that's a value that we might want to check out. And then the other place is at whenever pi r cubed minus 500 equals 0. Hold on a second. Okay, yeah. All right. Sorry, I was just checking my math. So so we're going to get critical values when r equals 0, and when r equals, if we set this equal to 0 and then solve, we would add 500, divide by pi, and then take the cube root, right? So we would get cube root of 500 over pi. 500 over pi to the 1/3 power is about 5.4-ish. Okay, well, so let's check these things. In order to determine if these things are maxima or minima, you know, I might want to do a second derivative test. Because otherwise it's kind of hard to tell what's going on. So I'm going to do a second derivative test. So second derivative is going to be 4 pi plus 4,000 r to the negative 3. If I plug in 0, the second derivative is undefined. If I plug in 5.4, I'm going to get a positive value. That means that at 5.4, the curve is concave up, which means this is a minimum. Okay, so this is a minimum. Okay, so I know that that's a minimum. Oh, you know what? The original function wasn't even defined when r is 0. So I don't have to worry about this one. Okay, so this is the only relative minimum, and therefore it is the absolute minimum. Okay, so there you go. We've found it. We found the r that minimizes the volume. this has to be it. I don't even care what the volume is because it didn't ask us to find it. It just asked us to choose the height and the radius. Well, we know that the radius has to be cube root of 500 over pi. What does the height have to be? The height has to be 1,000 over pi times this thing squared. So the radius is cube root of 500 over pi, right, which is approximately 5.4 centimeters. And height is 1,000 over pi times radius squared. And about how much is that? Let's see. 1,000 divided by pi times 500 over pi to the 1/3 power. That's about 58. Is that right? Hold on. 1,000 over pi. Oh, I forgot to square. Sorry, hold on. Okay, that's about 10.8. Okay, 10.8. Oh, that's interesting, right? So the height is about twice as much as the radius. Okay, so that's cool. Anyway, so there's that one. Okay, two more. I know I've been talking forever. This is probably the longest video I've ever done. But let's finish this out. So two more. This one says, find a point on the curve y equals x squared that is closest to the point 18, 0. So if I were to draw a picture of this, I mean, y equals x squared looks like this, right? And the point 18, 0, you know, is maybe like out here somewhere, right? 18, 0, something like that. So, so we're trying to find the point that's closest to this. You know, it's got to be the perpendicular line or whatever. You know, so it's got to be like that point right there. But let's call a point x, y. In fact, I'll do you one better. We know that y equals x squared, so really we can call it the point x, x squared, right? And then we can use the distance formula to get from this point to that point. So we can say the distance is the square root of 18 minus x squared plus 0 minus y. 0 minus x squared. Squared. That way it's all in terms of a single variable. Okay, so that's going to be, I'm just going to rearrange this. X minus 18 squared plus x to the 4th power. Okay. Well, in order to make the differentiation easier, notice that the square root's going to be maximized whenever the radicand is maximized. So really, you know, maybe I'll call this like, what should we call it? We'll call it something else, like maybe capital D, I guess. Capital D is x to the 4th plus x squared, 18 times minus 36x plus, what's 18 squared? 324. Okay, so I'm just going to maximize capital D, because if I can maximize capital D, or sorry, minimize, because I'm trying to get the closest point. So I'm going to minimize capital D, because if I minimize capital D, then I will have minimized lowercase d as well. All right, and really what I want to find is x, because if I can find x, then I can find the point, right? That's closest to 18, 0. So let's differentiate, right? So d prime of x is 4x cubed plus 2x minus 36. That's kind of nice. Well, I can take out a 2, so I'm going to set this equal to 0 and solve now. Well, actually, are there any restrictions? I don't think so. X could be anything, right? X could be any real number, so no restrictions really on x at all. Well, okay, so let's set this equal to 0 and solve. So 4x cubed plus 2x minus 36 equals 0. I can factor out a 2. I don't think I can factor that, so I think I have to use rational zeros theorem, right? And do factors of 18 divided by factors of 2, and I can make a list of the possible rational zeros. If you don't remember this from your pre-calculus days, I mean, you'll have to talk to me, I guess, so that I can run you through it. Possible rational zeros, though, are going to be factors of 18 would be like 1, so it would be plus or minus 1, 2, 3, 4 doesn't go in, 6 goes in, 7, 8, 9, 9 goes in, and then 18 divided by 1 and 2. So if you make a list out of this, you're going to get plus or minus, we'll say 1, 1/2, of course, 1, 2, 3. So you get all the whole numbers, 1, 2, 3, 6, 9, 18. But then you also get, 1/2. 2 divided by 2 is 1. 3 halves, right? 1/2, 3 halves, 6 halves, 9 halves, and 18 halves is 9. So those are all the possible rational zeros. Now, obviously, they're not all zeros of the polynomial, so now you have to go back through and test them. You can test them by either just plugging them into the polynomial and seeing if you get 0, or by doing synthetic division. And we like synthetic division because then that tells us what the leftover is. So I'm just going to try all the positive numbers first, just to see. So I have 2x cubed, 0x squared, x, and negative 18. And let's see if 1 works. 2, 2, 2, 2, 3, 3 doesn't work, right? So 1 is not a 0. What about 2? 2, 4, 4, 8, 9, 18, winner. Okay? So that means I can factor out an x. That means I can factor out an x minus 2, and I'm left with a 2x squared plus 4x plus 9. So I've got 2 times x minus 2 times 2x squared plus 4x plus 9 equals 0. So now here I can try to factor this. If it doesn't factor, I can use quadratic formula. I have a feeling that this thing does not factor. If we use quadratic formula, we would have negative 4 plus or minus the square root of 16 minus 4 times 2 times 9. That's not real. Okay, that's not real. So you don't get any real solutions from this piece. So your only relative extremum takes place at x equals 2. That's the only relative extremum. And since this polynomial is a degree 4 with a positive leading coefficient, I know that the end behavior does something like this, which means I must reach a minimum at some point in the middle. This has to be a minimum, right? This minimizes the distance d. So there you go. So what's the point? So we were supposed to find the point on the curve that's closest to the point 18, 0. It would be the point when x is 2. So it would be the point 2, 4, right? So the point 2, 4 is the point on y equals x squared closest to 18, 0. Okay, interesting. All right, last one, last problem. Here we go. This is a kind of a business thing or an economics thing, I guess. It says a liquid form of antibiotic manufactured by a pharmaceutical firm is sold in bulk at a price of $200 per unit. If the total production cost in dollars for X units is this, and if the production capacity of the firm is at most 30,000 units in a specified time, how many units of antibiotic must be manufactured and sold in that time to maximize the profit? So we want to maximize the profit. The profit would be the revenue that you generate when you sell X units of this, antibiotic, minus the cost that it took to produce them. So how much profit do you make? They're sold for $200 per unit. So if you produce X units, then you're going to produce a revenue of 200 times X. So the revenue, I'll say, is 200X, dollars. And the cost is here. So the profit, P of X, is the revenue that you generate minus the cost. Which we can simplify. I'm going to rewrite this in descending order. I've got a negative 0.003x squared. 200 minus 80 is 120, so plus 120x, then minus 500,000. Okay. So this is the profit, and we want to maximize the profit. Now, we're told that the production capacity is at most 30,000. So I'm going to say, X has to be between 0 and 30,000. So let's see if we can maximize this thing. P prime of X is, multiply that by 2, I get negative 0.006X plus 120. Well, that's not bad at all. If I set that equal to 0 and then solve, I'm going to get X equals negative 120 divided by negative 0.006. That's 20,000. Okay, so now I'm going to check this and the endpoints of the interval I'm looking at to see which of them is the maximum. Okay, so let's see. P of 0 is 0, 0, 0, negative 500,000. Okay, so don't produce 0 units. That means that you paid people and you rented facilities and stuff and you didn't produce anything. So of course you're going to lose $500,000. That would be bad. What about if we produce 20,000 units? This would be 200 times 20,000 minus 500,000. Oh, I don't know why I'm trying to plug it in here. Let me plug it in here. So this would be negative 0.003 times 20,000 squared plus 120 times 20,000 minus 500,000. Okay, that's 700,000. That comes out to $700,000. And then finally, what if you produce 30,000 units? Then your profit is $400,000. Okay, so there's the winner, right? So what was the question we were supposed to answer? How many units must be manufactured and sold to maximize the profit? So we should manufacture 700,000 units. that's, or not 700,000, sorry. That's the profit that you generate, but you should manufacture 20,000 units, and that'll generate a profit of $700,000. Goodness gracious. All right, that's the end. I think I've been talking long enough.